Hi guys, in today's video I would like to show you this 2-axis gimbal that I've made. So this gimbal uses an Android app to read an accelerometer data, and then it sends it via Bluetooth to this STM board, which is down here, and it controls these servos. So this gimbal is capable of controlling the roll of the camera and the pitch, as you can see. And this gimbal knows its limits, so it doesn't crash. So if you tilt it too much, it eventually stops. But in practical terms, this is quite useless. As you can see, it's quite shaky, it's slow, but for tutorial purposes it is good enough. And then, as you can see, I have here exit app button, because this app is capable of running in the background. So even if you minimize this app, it still works. And I can launch a camera, and this way you can use it as a gimbal. But as you can see, this can give you more of a motion sickness, and it's quite useless, but let's get started. I would like to explain how this works. And as you can see, I can try to exit this app, and now it's off, so it doesn't control the servos anymore. So let's get started. So one of the reasons why this gimbal is so laggy and so slow, it's because it uses servos, which are on their own quite slow, and they are controlled by PWM signal, where by changing the duty cycle you tell the servo what position it should keep. So I can tell where the servo it should be at, but if I gave it a command to go from the 90-degree position to the 0-degree position, it takes some time to that servo to get there, but I have no clue where the servo is at. So I have no idea if it is aiming there, going there to that position, or if it is already there. So I have no feedback from that servo where it is at. So that's why I've decided to periodically give the servos a new update position, and I change this duty cycle just slightly. So I change it just a little bit and a little bit more, and I tell the servos that way that they should turn slightly to the one side, or even more, or just stay there, or to move to the other side, or just step by step. And this top servo, which handles the rolling of this camera, it's quite easy, because it turns the phone around the center of mass. But this bottom servo that manages this tilt, it changes the pitch of this gimbal. It has to generate quite a bit of torque, because as you can see, this system above it has maybe 200 or 250 grams, and it is quite far from this axis of the servo to the center of mass of the phone. So it has to fight a lot, and this servo is eventually way too slower than this top one. So That's why this bottom servo has a lot of struggling. And I have update rate 20 times a second, so it's every 50 milliseconds. Every 50 milliseconds I send a new command from this smartphone via Bluetooth to this STM board. And these servos on their own, they have update rate 50 times a second, 50 hertz. So it's every 20 milliseconds. So that's how I manage this. And this update rate from the smartphone is basically I came up with it just by trial and error. So I was just trying to find the correct update rate to keep it as smooth as possible, but it's quite difficult and I wasn't able to make it really smooth, so that's why it ended up so shaky. So that's all to this system, how it works. And now let's move on to the model. So as you can see, the first part is this STM model for this gimbal base, which is basically a handle with a case for the power bank. And in this corner, here's the STM32 board. And over here, I've glued the mount for the servo motor. And so this part is glued on top of that. And this is where the first axis of the servo is. So it is basically this part down here. And on top of that, there's this another mount for this servo, this bottom one. And on top of that, I've glued this part that looks more like a meat grinder, but whatever. But it holds this top servo. And on top of that, I have this case for the smartphone. So that's how it is all glued and mounted together. And this whole project is already uploaded on my GitHub. And now let's move on to this Android Studio project. So as you can see over here, I have just two objects. One of them is this text view, where I plot the data from the sensor and the pitch and the roll. And over here I have a button to exit an app, because it can run in the background. And over here, by this command, I lock the screen orientation to the landscape. And I have it also in this manifest file. And over here, I have a button exit, and when I click on it, this way I exit this app, because this app can run in the background. And up over here, I have used accelerometer to read the data, but in later Android phones it is better to use gravity sensor, so you can change it to type _gravity. So it is over here and over here. And I have implemented directly to the class this sensor event listener. So that's why I override this on sensor changed and on accuracy changed. So this way I handle this. And when I get the new data, I basically read this event and assigned those values to X, Y, and Z, and calculate the roll and the pitch. And I have up here the limit of 3 degrees, so I can tolerate plus minus 3 degrees to be considered as a perfect level. And my update period is, as I mentioned, 50 milliseconds. So let's get back here. So when the pitch is greater than the limit, which is 3 degrees, I tell the servo to move to one way, and for the pitch and for the roll. So this way I tell the servo whether it should turn to the one side or turn to the other side. And if it is within this tolerance, then none of these conditions are triggered, and the 0 tells that the servo it should keep its position where it is at. And over here I just put those messages, put these strings together, and add their end of line character and send it. So when I'm connected, I just send those data. So that's basically it. And over here at the top, I just check and verify whether the 50 millisecond period already passed or not, and then I update the time. So that's how this update rate works. So now we can move on to the STM32 project, and I'll explain how that works. So over here I have 2 GPIOs for the LED and for the Bluetooth reset pin, and this UART2, which is over here, is set to 9600 bits per second, or baud, and yeah, I have enabled global interrupt to receive the data from the Bluetooth module. And over here I have timer 4, which controls the PWM. So I have channel 4 and channel 3 activated for those 2 servos, and its update period is 50 Hertz every 20 milliseconds. And I have also enabled here global interrupt. I'll explain this later in the code. And to help this UART receiving, to handle incorrectly received messages, etc., I use this timer 2 that launches itself every 20 milliseconds. And if I start receiving a message and it takes too long, I basically cut the receiving off. So that's basically it. And I have set up the clock frequency basically to the maximum possible. So that's all for this MCU configuration. And over here I have this part of the code that initializes these servos, this timer and these PWM channels. And then I reset the Bluetooth module, name it as a Gimbal. I clear the buffer, start this timer 2 that helps receiving to the UART, and then I enable this UART interrupt, and eventually then I turn on the LED that everything is initialized, And that's all, and I handle everything in interrupt. So as you can see, this infinite loop is empty. And over here in my library, I have set up the limits for the pitch on and for the roll. So that's why those servos don't crash. And I have just a few variables, pitch, roll, which are values for the PWMs, the buffer for receiving messages, the timer count that counts when the receiving starts, and if it takes too long, it stops the receiving. And this buffer index that tells how many characters have been received. And I have two functions over here. So that's basically it. So here are the variables. So these values might be different for you because those servos are also not accurate. But these values keeps those servos straight when I reset the STM board. And over here, I just verify whether the length of the buffer is 3, because I receive only 3 characters, plus, minus, and end of line, for example. So over here, I verify if on the zeroed position there's plus, minus, or 0 received, and also on the first position. And position number 2, technically it's the third position, if there's end of line character. So this way I verify whether the received message is correct or not. And afterwards, then I check if I can increment or decrement the pitch and the roll. And then if it is too much, I just set the pitch to the maximum value or to minimum. So that's basically it. And everything else is handled over here in interrupt. So I will start with this UART2 interrupt handler, where I received character by character, and if I receive end of line character, I launch this message handler that I was describing. And this timer 2 checks whether I've started receiving something. So when the buffer isn't empty, it means I've received something. And if I don't receive end of line character until 100 milliseconds, then I launch the message handler that will eventually clear the buffer. So when I properly receive the message, it should contain end of line character. But if it takes too long and I haven't received one, I just launch this message handler anyway. And over here, I always verify whether the pitch or roll is within the correct range. So in this case, I can correct it. And this is the timer 4 that handles the PWM. So every time the interrupt is launched, I can calmly, without a problem, update the duty cycle for the pitch and the roll. And this way I control those servos. So that's basically it for this code. So I hope everything was clear and explained. And everything is available on my GitHub with plenty other projects. So that's all for explaining. And in the end of the video, I would like to show you some shoots from the outside. So thanks for watching.